In this second video on Lewis structures, what we want to do is look at some cases that are a little bit more complicated, look at cases called resonance structures. So we're going to look at some of the more complex Lewis structures here. Remember from the last time, we're looking at the valence electrons of each atom. We're looking at making sure that each has an octet, 8 valence electrons, unless it's hydrogen, which needs a duet or 2. Start with single bonds and then work your way up. So 2 carbons for 8. 4 hydrogens, a total of 12 electrons. Now I've got the 2 carbons. I'm going to bond them together first. I can attach hydrogens. Now if I start by attaching hydrogens here, that uses 8, 9, 10, 11, 12. That's not going to be stable because this carbon only has 6 electrons, so that can't work. Keep my carbons together. Try putting 2 on each. I still have 2 more electrons to work with, so at most I can get 7. So that's not going to work. So I'm going to have to use a double bond. So I'll double bond the carbons. Now I've got hydrogen on each of the 2 carbons. Now each carbon has 8. Each hydrogen has 2. If you were to do this with dots, it would look like this. Now, if you look across the periodic table to our non-metals, you can generally see the types of bonds that are going to be occurring. If you take carbon, has 4 valence electrons. Nitrogen has 5. Oxygen has 6. Fluorine has 7. So this one has carbon has 4 valence electrons. So this is usually going to form 4 bonds. Something in the nitrogen family has 5 valence electrons. It needs to gain 3 more, so it will usually form 3 bonds. Oxygen has 6, so it will usually form 2 bonds. And the halogens usually will form 1. Now this is not always the case, but is usually the case. And you can see here, each carbon has 4 bonds, each hydrogen has 1. Now let's look at SO3. Sulfur has 6 valence electrons. Oxygen has 6 times 3, 18. We have a total of 24. So if I start with sulfur and bond it to each of the oxygens, that gives me 6 of my electrons, so I have 18 more to work with. 2, 4, 6, 8, 10, 12, 14, 16, 18. So I end up with this oxygen being stable, the oxygen here in the middle being stable, the left oxygen only has 6, and this sulfur only has 6. Now, oxygen usually likes to form 2 bonds, so this is not following our pattern that we saw before. We need a way to get 2 of these electrons so that we can, I think I may have counted wrong. 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22. Sorry, there's 24 electrons. That's my mistake. So each oxygen's stable here, but the sulfur is not. Or we could have put 2 on the sulfur and had the oxygen not be stable. So we're going to need a double bond. And what we see here is pick one of the oxygens and double bond it. The question is, how do we know which oxygen to double bond? Now, for drawing the Lewis structures, it really doesn't make a difference. But because there's 3 equally good possibilities, we could double bond to the lower left one, or we could double bond to the lower right one. Now, what you will find is that when we have covalent bonds, single bonds are going to be longer, bigger distance between the atoms than double bonds, which will be longer than triple bonds. What they find when they actually study SO3 is that each of the bonds is in between being a double bond and a single bond. So you actually get it rotating, you can kind of think of it as rotating through all three possibilities as being partially double bonded and partially single bonded. So it rotates through these three possibilities for the bond with oxygen. We refer to this as resonance. When there's more than one Lewis structure that can be drawn for the molecule. For example, you could have an odd number of valence electrons. Or it could be fluctuating between single and double bonds, like we saw with SO3. So there are exceptions like this, known as resonance, where we see fluctuations between double and single bonds, or double and triple bonds. Let's look at some more cases. SO4 2-. Now we have 6 sulfur, 24 from oxygen, plus the 2-, which adds an extra 2 electrons. So we have 32 electrons. If I put the sulfur in the middle and bond it to each of the oxygens, that takes up 8, 9, 10, 11, 12, 13, 14, 16, 18, 20, 22, 24, 26, 28, 30, 32. This would give us a case where we have everything stable with only one bond to each. So it's an exception to that idea that sulfur and oxygen usually have 2 bonds, but it is stable. Anytime we have an ion, though, we must put it in brackets and put the ionic charge on the outside. And one final one, let's look at HCN. H has 1 electron, carbon has 4, nitrogen has 5, so we're going to have a total of 10 electrons. If we bond hydrogen to carbon to nitrogen, that takes 2, 4, you could put 6 and 8 on top of the carbon, then that'll leave us with 2 on nitrogen, which wouldn't work. Now we know in this case we're going to think about the number of bonds they'd like to form, because that's usually a helpful way to start. Carbon likes to form 4 bonds. Nitrogen likes to form 3 bonds. So if we could have 3 bonds here, that would give us 2, 4, 6, 8 of our 10, leaving us 2 for the nitrogen, 10 electrons, 8 around nitrogen, 8 around carbon, 2 around hydrogen. So here's a case of a triple bond. Lewis structures are something that require a lot of practice, so we'll be spending a lot of time in class working with these